Today we're going to be talking about Tay-Sachs disease. Tay-Sachs is a rare autosomal recessive genetic disease. It is caused by a beta-hexoaminidase A deficiency that leads to a progressive deterioration of nerve cells and physical abilities.
The most common type of Tay-Sachs disease manifests itself in infants 3 to 6 months of age. Affected individuals rarely survive into their childhood. Juvenile and adult forms of Tay-Sachs are quite rare and often exhibit less severe symptoms compared to the infantile form.
Symptoms from Tay-Sachs include loss of basic motor function such as turning over, sitting, and crawling, and a cherry red spot in the eye. Later symptoms include seizures, loss of vision and/or hearing, as well as paralysis.
Symptoms of Tay-Sachs in adults and juveniles include muscle weakness, loss of motor coordination or ataxia, and other issues with movement, speech, and mental illness.
Although rare, Tay-Sachs disease is most often observed in secluded communities such as the Ashkenazi Jews, French Canadians, Cajuns from Louisiana, and the Amish in Pennsylvania.
Studies indicate that the frequency of this disease in Ashkenazi Jews who are born to affected parents and grandparents is 1 to 27. However, among Sephardic Jews and all other non-Jews, the disease incidence has been observed to be nearly 100 times lower, corresponding to a tenfold lower carrier frequency.
We are now going to talk about the relationship between phenotype and the genome for Tay-Sachs disease. Tay-Sachs is caused by a mutation in the HEX-A gene. In humans, HEX-A is located on chromosome 15, and the most common mutation is a 4-base pair insertion in exon 11.
If an individual is homozygous recessive for a mutated allele, they will fail to produce the enzyme beta-hexoaminidase A. This enzyme is normally located in lysosomes and plays an essential role in the breakdown of a fatty substance in neurons called GM2 ganglioside. In the absence of this enzyme, GM2 ganglioside within neurons will reach toxic level. This continuous increase in ganglioside toxicity eventually leads to the destruction of neurons and brings about the symptoms of this disease.
In order to elucidate the mechanistic basis of Tay-Sachs, we chose the mouse as our model organism. The mouse is ideal for this study because it is a mammal, and we can easily generate a knockout of the HEX-A ortholog using the CRISPR-Cas mechanism.
As Alan mentioned, we're going to be using the CRISPR-Cas mechanism to generate HEX-A knockout mice. We will then screen for subjects that exhibit uncoordinated motor behavior and assay GM2 ganglioside levels in their neurons. If uncoordinated subjects show a higher than normal level of gangliosides, we can confirm the essential role of the HEX-A gene and its product, beta-hexoaminidase, in the breakdown of gangliosides in neurons.